Hello friends, this is part 3 of physics paper mechanics C2 solution, right, for the BSc first SEM of the year 2021 for the physics honors students. This paper is said by Dibrugarh University. So in part 2 we have solved up to the question number 3D, right? Up to question number 3D. We have solved up to question number 3. Now in this video we're gonna start from the question number 4A, right? So before we start, please subscribe the channel and hit the like button and share with your friends, and also press the bell icon so that you get notified when new video will be uploaded, right? So let's start. So here is the first question, that is question number 4A. So I have already made a video how to reduce two body problem to single body problem. One video is available in my channel, so I have provided the link in the description box. You may check the link given in the description box. I have written question number 4A answer, then I have given the link, so you may go through the link, or you may check the playlist with the name classical mechanics. There you will get that lecture. Okay, so either you can go to description box, then check the link. Okay, so there I have given the link of the video where I have made the video on this topic. Okay, now let's move on to next question. So this is our next question. So state the Kepler's law of planetary motion. So we have already written this statements in while we are solving 2019 paper. It was asked in 19 also. So let's go to next part of this question. So that how the law of gravitation can be deduced from the Kepler's law, and why is the constant of gravitation is called universal constant. So let us solve it. So here, law of gravitation from Kepler's law. Now assuming the earth is revolving around the sun with angular velocity omega, which is equal to 2 pi by t. T is the time period here, and m be the capital M be the mass of the sun, and small m be the mass of the earth, and small r be the radius distance between the earth and the sun, right? Here you say this is the sun, suppose, and its mass is capital M, and this is the earth with the mass small m, and radius distance between them is suppose small r, right? Then the centripetal force acting on the earth will be given by Fc. This to represent centripetal force I have written Fc. So here that's going to be given by m omega square into r. Okay, now let's move on to next slide. Now you see the centripetal force. I have written the expression again. Fc is equal m omega square r. This is the expression for centripetal force, and we know that omega is equal to pi by capital T, 2 pi by capital T, right? So if you put this one here, then you will get this result. Fc is equal to m 2 pi by t whole square r, right? And squaring this, we have got this expression. This is suppose equation number 1. So let me take this is equation number 1, right? So now according to Kepler's third law, so if you consider if you take the third law, that is what time period square of the time period is equal to not equal to, is proportional to the cube of the distance between these two star and planet, that is sun and earth. So now you see, if you make it equal, then there must be a constant of proportion, that is we have taken k here, and using equation number 2 and 1, using these two equations, we have got Fc is equal to this expression here. You see this r cancels r cube to give r square, right? Then this is the expression we have got. Fc is equal to, that is the centripetal force acting on the earth. Now the gravitational force between the earth and the sun, that must be equal to this centripetal force. That is, I have considered that capital F represents the gravitational force only, and Fc represents the centripetal force. And then I have written the expression that we have got here for Fc. Fc is equal to 4 pi square by k into m by r square. So I have written that here, and this is suppose equation number 3. So from here you see this part is constant, right? This part is constant, so F is directly proportional to m by r square, you can write, okay? And this is constant, right? 4 pi square by k, this is what? Constant. And this constant is proportional to the mass sun, capital mass of the sun, capital N. And if you make it equal, then again you need a constant, that is capital G, that is called universal gravitational constant, right? Now from this equation number 4 and equation number 3, from these two equations, that you can write that F is equal to, that is gravitational force between the sun and the earth, you can write F is equal to capital G, capital M, small m by r square. So this is the law of gravitation, right? So that's how we can obtain from or using the Kepler's third law, that's how we can obtain the Newton's gravitational law, right? So now you see the next part of this equation is here, you see why, here you see why the gravitational constant, the constant of gravitation is called the universal constant. Let me tell you here. So this is the answer here. You can see the value of capital G is constant for any object in the universe, and it doesn't depend upon the medium between the particles. Thus the constant of gravitation is known as universal gravitation constant. So hope you have got it. Now let's move on to the next question. So now question number 4b, what is damp oscillation? That definition we have already written in 2019 paper, so that's why I have not written here again. So now next part of the question, deduce the differential equation of motion for it and express the frequency of oscillation. Now you see we are going to deduce the differential equation, and we're going to find the solution of the differential equation. Here you see frictional or damping force that is directly proportional to the velocity of the oscillating object, okay? And Fd I have written to represent damping force or frictional force, and that is proportional to negative dx by dt. Dx by dt represents velocity, right? And these are oppositely directed, that's why negative signs comes here. And to replace this, to make it equal, to write equal, so we need a constant here, minus b dx by dt. Here b is the constant here. Total force acting on the oscillator, that's going to be minus kx, right? This is k is spring constant here, minus b dx by dt, where k is called spring factor. Suppose you have a oscillator, this is a spring, and you have a mass here on the surface, and this is oscillating to and fro motion. And here you see this minus kx, this force is provided by this spring, due to this spring, and this minus b dx dt is due to the friction and maybe air resistance. This is the damping force, right? So hope you have got this, how we have got the total energy, a total force acting on the oscillator. So that's why using Newton's second law, according to Newton's second law, that mass into acceleration, that is second order derivative of displacement, that is x, with respect to time t, that gives acceleration, and mass into acceleration, that is that's going to be the force acting on the oscillator. And we have got here that for total force acting on the oscillator is this, and that's why these two must be equal, right? So hope you have got this. Then if you simplify this equation number 1, then you will get this equation number 2, right? So after simplification of equation number 1, So what we have done, we have brought these two terms, we have shifted these two terms, negative terms, to the other side, and then we have divided each term by m, right? So we have got this equation. Now consider b by m as 1 by tau, where tau is the time of relaxation time, and k by m is your, you know, omega naught square, right? This is omega naught square, which represents natural angular frequency. Omega naught represents natural angular frequency. Let's move on to next slide. So here is the equation that I have written again. This is equation number 3, and its general solution is given by this expression, right? So where beta is equal to given by this. Now angular frequency omega will be given by omega naught. Omega naught is the natural angular frequency. Omega naught is square minus 1 by 2 tau whole square, and after putting these values of 1 by tau here, that what we have considered 1 by tau is equal to b by m. If you put this one here, we have put 1 by tau is equal to b by m as we have considered, then we have got this expression. So this is the frequency of the motion, right? Now the frequency of the motion, this is the angular frequency. Now frequency of the motion, n, will be given by omega angular frequency divided by 2 pi, right? And if you put the value of omega here, then you will get this expression for frequency of the motion, right? So hope you understood this. Now let's move on to next question. So next question, here you see, what is simple harmonic motion, and deduce a differential equation of motion and find its solution, right? So first we have to define simple harmonic motion. What is simple harmonic motion? So here you see, this is the answer to the next part of the question that you can see. So now let me define the simple harmonic motion. Simple harmonic motion, its definition. What will be its definition? So it can be defined as, if the acceleration of a periodic motion from the of a particle is such that it is directly proportional to its displacement from the fixed point and is always directed towards the fixed point. Directed towards the fixed point. The motion of the particle is is said to be simple harmonic motion. Simple harmonic motion provided the displacement from its equilibrium position is small. Provided the displacement from the equilibrium position, that means the fixed point, equilibrium position is small, right? So this is called simple harmonic motion. So hope you have understood this. Now for the next part, let us go to next part, deduce the differential equation of motion and find its solution. So here you see, let us consider a particle of mass m. So here mass is small m. We are talking about a particle of mass small m. Suppose this is small m executing simple harmonic motion, and if x is the displacement of the particle from equilibrium position at any instant, suppose t, at any instant t, then according to the definition of simple harmonic motion, the restoring force acting on the particle is given by, so that the restoring force must be directly proportional to x displacement. F is directly proportional to x displacement. Here we have got the definition that in a periodic motion particle is such that it is directly proportional to its displacement from the fixed point. Fixed point means here they are talking about the equilibrium position, right? And to make it equal, we need a constant. So f is equal to, we have got minus k x, right? Because you see, suppose you have an oscillator, you have such system that undergoing simple harmonic motion. This is mass m. So when it will move forward, this spring will pull it the back, it is pull this mass backward. So that's why these are opposite. So that's why here this negative sign comes, right? So here k is the constant of proportionality, and negative sign indicates that the direction of force is opposite to the increasing this displacement here. And acceleration is given by second order derivative. If x represents position, dx by dt represents velocity, and second order derivative represents acceleration, right? So that and mass into acceleration, if m into second order derivative of x is this is acceleration, represents force, which is equal to, in this case, minus kx. So that's why we have got m second order derivative of x with respect to time t is equal to minus kx. So we have got m second order derivative of x with respect to time t is equal to minus kx. That's what we have got. And this if you simplify this equation, you will get this equation, right? This one. So here if you substitute k by m by minus omega naught omega naught square, then we get this differential equation. So this is the general differential equation of motion of simple harmonic oscillator, right? So hope you have understood this. Now let us consider the solution of equation number 1 as x is equal to a to the power alpha t, a into e to the power alpha t, e to the power alpha t, we have considered that way. So if you consider so, then this gives that if you find a second order derivative, right? So that means you have taken the solution this way. X is equal to, you have taken x is equal to a e to the power alpha t. If you differentiate it dx by dt with respect to time t, then it must give you a alpha e to the power alpha t, right? Its derivative. And if you differentiate it again, dx by dt, if you find a second order derivative, if you differentiate it again, then it will give a alpha square e to the power alpha t. So hope you have understood. That's why we have got this expression, right? Now if you substitute this in equation number 1, if you substitute what you have got, the second order derivative of x, right? So this is equation number 1. So let me write here in red color or black color. This is equation number 1. If you substitute this value, the second order derivative of x with respect to t, that is a alpha square e to the power alpha t, if you put here, and if you put x is equal to this one, right, then you will get this equation. Sorry, not this one, this one. You will get this equation, right? This is equal to 0. Now from here, if you take that a e to the power alpha t, if you take common, a e to the power alpha t, if you take common, then inside the bracket you have got alpha square plus omega naught square, which is equal to 0. And as you see, a e to the power alpha t cannot be equal to 0. Therefore this term within the bracket must be equal to 0, and which gives that alpha is equal to plus minus I omega naught, where I is the complex number. So hope you have understood. Let me mention one more thing here, that that is all about this omega. What is omega here? So here you see omega naught, not only omega, this omega naught you have got here, that this omega naught, right, omega naught is square. So omega naught is the angular frequency here, angular frequency of the oscillator, right? So now let's move on to next slide. So we have got the value of alpha, that is plus minus I omega naught. So if you see here, we have two possible solutions. One is x is equal to a e to the power I omega t. As we have considered the solution x is equal to a e to the power alpha t, and we have got the value of alpha. There are two values we have got. One is positive I omega naught, right, and one is negative I omega naught. This is plus minus I omega naught, means there are two solutions. One is positive I omega naught and another is negative I omega naught. So that's why we have got two possible values here, right? So therefore any linear combination of these two solutions will also be a solution of equation number 1. So what was the equation number 1? Let me rewrite the equation here. This is the equation number 1, right? So let me write the equation number 1 here, that second order derivative of x with respect to time t, right, then plus this omega naught square x is equal to 0. So this was the equation number 1, right? This is equation number 1. So it's as we have got two possible values, x is equal to this one and this one, so linear combination of these two solutions will be the solution of this equation that is given by this. So here a1 and a2 are constant. So equation number 2 also may also be written as, this is the equation number 2. This equation also can be written as this, right? Because you see here what we have applied, e to the power I omega naught t, that's going to be equal to cos omega naught t plus I sin omega naught t. That's an identity, that's a formula, right? And we have applied that in equation number 2. So that's why we have got this. And after simplifying, here you see separating the real and imaginary parts in this solution, we have got x is equal to a3 cos omega t omega naught t, a4 sin omega naught t. So a3 is a1 plus a2 and a4 is a1 I minus a2 I. These are new constant. So this is equation number 3, right? So now let a3 is equal to small a sin phi, a4 is equal to small a cos phi, so that you can write x is equal to this a sine phi cos omega naught t and a cos phi sine omega naught t. That means if you put this a2 and a4 values in this equation number 3, then you should get this, right? And here you see, if you apply the if you notice it, if you carefully if you see the right hand side carefully, then this is in this form. Sine a plus b formula is applicable here, right? And that is why we can write a sine omega naught t plus phi. So this is equation number 4. This is equation number 4, right? This is equation number 4, already written here. It's too far, that's why I have written here. So this is equation number 4. Let me write it clearly. Equation number 4, right? So here a is the maximum value of displacement called amplitude of the oscillator, and phi is the constant called initial phase or phase constant, right? So now if you put that phi is equal to delta pi by 2, delta plus pi by 2 in equation number 4, in this equation, that means they are talking about this equation number 4, equation number 4. In this equation, if you put phi plus pi by 2, phi is equal to delta plus pi by 2, then this 4 can be expressed in this form, right? This equation number 4 becomes this. So this is suppose equation number 5. Now here you see the either of equations, this 2, 3, 4, 5, this all represents the solution of equation number 1. So hope you have understood this topic. Now let's move on to next question. So here's the next question, question number 5. Explain the fictitious force and show that the centrifugal force is fictitious force. So here you see, let us consider, this is the answer. Let us consider two systems S and S dash, and this S dash is moving with an acceleration a0 relative to the former, that means relative to this S. If we consider that the first frame to be inertial, we have considered this S frame with the origin O be inertial. So then the second frame will be non-inertial and vice versa. That means if you consider this S as an inertial, then this S dash must be non-inertial, and if you consider this that S dash is inertial, then this S must be non-inertial. That is what they are trying to say. So here you see, this is the diagram. Hope the diagram is clear, or if it is not clear, let me just make it clear, make it visible. Wait, just give me a few seconds. So hope it's clear now. So this is X and X dash are there. This X x-axis of these two frames coincide, we have considered that way, and this is its origin of the system S, and this is the O dash is the origin of system S dash. O dash is the origin of system S dash, and here we have considered the ith particle of mass m moving with ai acceleration, and we have considered the acceleration of this frame is a0, right? This S dash frame is a motion, is undergoing a motion with acceleration n. We have considered that way. So hope you have understood. Now consider a particle of mass m that I have already said not acted by any force in the system S. Then the acceleration of the particle in the system S will be 0. So with respect to this system S, the force on this particle of mass m, there is no force acting on this particle on mass m is 0 with respect to this S. So therefore acceleration of this particle with respect to this frame S is 0, but the particle will seem to have an acceleration negative a0 relative to S dash, right? Thus the force acting on this particle will be minus m a0, right? Will appear to be acting on the particle to an observer in the system S dash. If we have an observer in the system S dash, then he will observe that force acting on the particle of mass m will be m minus m a0. So a0 is the acceleration, right? So here you see, while the observer in the system, now you see if you consider this one, these are the two systems, right? This is S and this is S dash. So you have a particle here. This particle is at rest with respect to this system S, and but as this frame of reference is moving with an acceleration a naught in this direction, so in opposite direction this particle must have an acceleration negative a naught, right? So hope you have understood this. So while an observer will observe from this system S dash, from this system, so he will see that this particle of mass m, which is at rest with respect to this system, is moving with acceleration minus a naught. So hope you have understood these things, right? Now you see, S dash will not observe any force acting on that. So that observer on S dash will not observe any force acting on the particle. So I think there is a printing mistake. Here you see they have written in this way. Let me show you again. So you see, thus the force acting, the force minus ma naught will appear to be acting on the particle to an observer in the system S dash, already written S dash. Then they have written again, while the observer in the system S dash will not observe any force. So I think, actually not I think, it must be S only. This should be S, not S dash. Okay, make it correction. This is S and here is S dash, because this one is S dash, that's correct, right? This S dash is correct, but it should be S, because you see, the observer on this system will observe this force, but observer on this system S will not observe any force, because with respect to this frame S, this particle is at rest, right? So such kind of force that appears due to the acceleration of this frame of reference is called fictitious force or apparent force, or you can say pseudo force. So now you see, consider the particle has an acceleration ai. So we have considered a particle has an acceleration ai. Okay, so that means this particle also moving with an acceleration, we have considered that way. So now you see, as observer from the system S, then according to Newton's second law of motion, the force acting or applied on the particle is given by Fi is equal to mai. So initially we have considered that way, that this particle, you see, so let me clean this a little bit. So initially, so here in above explanation we have considered that this particle is at rest with relative to this system S, relative to this system S, right? But it has an acceleration due to the motion of the next frame, that is S dash. It has an acceleration minus a naught. But now we have considered this force, this particle has itself an acceleration. It is an accelerated particle with respect to the frame S as well. With respect to the frame S also, it has an acceleration ai. So the force acting on this particle of mass m, according to Newton's second law, with respect to this frame, will be given by Fi. Here F is written bold, means it is a vector, so m ai. So this is the force. Now acceleration of the particle relative to the system S dash. Now you see, this system S dash is moving with an acceleration a naught, and this particle of mass m is also moving with acceleration ai. So therefore relative acceleration, that means relative to S dash, what will be the acceleration? The acceleration of the particle ai minus acceleration of the system S dash, that is ai minus a naught, right? This is what we have got, a I vector minus a naught. So hope you have understood this. So here this is taken as equation number 1. This above equation is taken as equation number 1. Now let's move on to next slide. Now you see, therefore the total force acting on the particle as observed by the observer in the system S dash. Okay, total force acting on the, because you know relative to S dash we have got acceleration ai minus a naught, right? So this is the acceleration. If you multiply here mass, then you will get the force, right? F dash, right? So this force will be observed by an observer in the system S dash, right? So hope you have understood this. So now these are vectors. So where you see the bold letter, that means that is vector. So remember that, right? Thus, in addition to the force Fi, the particle experiences an additional force, that minus m a naught, in non-inertial frame. This additional force is nothing but fictitious force. Thus fictitious force is given by Fp. This is equal to m a naught, right? So negative mass into acceleration of non-inertial frame, right? So now let us move on to the next part of the question. Here you see centrifugal force is also fictitious force. Now here you see, let us consider a point of mass m at rest in a non-inertial frame, so that in this frame a is equal to 0, right? So that means we have considered two frames, right? This is S and S dash. S dash was moving with a naught acceleration, right? S dash is moving with respect to S dash is moving with an acceleration a naught. So now we have considered a point of mass m which is at rest with respect to non-inertial frame, that is S dash, right? So that now the acceleration of this particle is 0. The non-inertial frame uniformly rotate about a fixed point. Suppose now this time this inertial frame is being rotating around this origin O dash. Suppose it is rotating like this, okay, with respect to inertial frame, right? With respect to, this is the S is the inertial frame, S dash is not inertial, this is non-inertial frame, and it is rotating, suppose, right? It is not moving forward, it is rotating like this. This is the S dash here, this is Y dash, this is X dash, and this is rotating. Now this S dash frame is rotating, right, about a fixed point with respect to the inertial frame. The acceleration of the point mass with respect to this inertial frame may be written as, so is given by a naught is equal to minus omega square r. This is equation number 4. So let me explain the situation again. So the particle we have considered, so here is the inertial frame, suppose S, this is the inertial frame S, and the non-inertial frame is now rotating, that is S dash, it is now rotating. Now we have considered a particle of mass m. This m is at rest relative to S dash. That means if this is in motion, this S dash is rotating with angular frequency omega. Suppose if this S dash is in motion, then to be at rest relative to S dash, this mass m must be also moving with this frame. So that means this mass have an acceleration with respect to the inertial frame S. As we have taken this particle of mass m, is at rest with respect to the non-inertial frame, which is S dash, right? So for this frame S dash, this acceleration of this mass a is equal to 0, and for the mass for the acceleration for the relative to this S frame, inertial frame, its acceleration is a naught. You can consider that way. So here omega is the angular velocity of S dash, you can consider that way. Now remembering that a is equal to 0, that means the acceleration of the particle with respect to the frame s dash non-inertial frame a is equal to 0, because we have taken this mass m is at rest with respect to the non-inertial frame. We have imagined that way. So a is equal to 0. Then the equation number 3 lead us to this equation, right? So let me tell you how. Okay, let me tell you how. So here r is the position vector of the particle of mass m, right? So here you see in this equation f dash, so here this f dash is nothing but the fictitious force. Here you see m, so ai, so here you can consider ai is 0 now, minus a naught. So this force, this is the fictitious force fp, you can consider that's going to be equal to minus m a naught, right? Now if you put here this force f, this force f, right, that's going to be equal to minus fp. So if you replace the fp by minus ma, that's going to be plus m a naught, so not a naught, right? So if you put this fp here minus m a naught in this equation, that means what we have, what we are writing here, force f, that's going to be minus fp. So if you put here minus m a naught, that's going to be, just let me clean this, minus m a naught, then it's going to be m a naught, right? So here you see m a naught is, if you use equation number 4 here, right, if you use equation number 4 in this case, this equation number 4 here, instead of a naught, if you put minus omega square r, then this is gonna be equal to minus m omega square r, right? So you will get this. So that's how we have got this. So this is equation number 5 we have given. So this is the fictitious force fp, which is equal to m omega square r, which is also the centrifugal force. So that's how we can prove that centrifugal force is also a fictitious force. So hope you have understood this. Now this is our next question. What is Coriolis force? Discuss the effect of freely falling body. The Coriolis force is an inertial force that acts on an object in motion within a frame of reference that rotates with respect to an inertial frame. So this is the definition, and here the next part of the question is this. This is the next part. So suppose we have considered here the earth is rotating with an angular velocity omega, right, angular velocity omega, with north and south as the axis of rotation. That means this is the earth. So this is so let me draw it clearly. So suppose this is your earth, and this is east, this is west, this is north, and this is south. So we have taken the axis of rotation as north and south. So it must be rotating like this, because sun rises in the east and goes to west, right, set in west. So here you see this is the axis of rotation, with rotating with angular velocity omega, right? We can consider that way. So now let x dash, y dash, z dash be the axes along the so this is, we have considered that x dash, y dash, and z dash, we have considered that way, be the east, north, and vertical direction. That means here you see we have considered that way. This is the east, that is x dash, and this is the north, not north, this is suppose the vertical one, z dash, and the north, towards north we have suppose y dash, right? So this is the earth, and we have assumed that way, right? So the respective unit vectors will be I cap, then j cap, and k cap, right? So be the unit vectors along x dash, y dash, z dash, z dash axis respectively. Let the body of mass be falling freely on the surface of the earth. Let v dash be the velocity of the body at any instant t. So towards the earth a body is falling freely, right? And velocity with respect to you see at any instant with respect to this frame x dash, y dash, z dash, be suppose v dash, right? We have to assume that way at time t, right? So now this angular velocity omega vector, that's going to be equal to, so this omega vector will be equal to omega cos lambda zs and plus omega sine lambda kds. These are the unit vectors, right? So now let me write this one properly. So omega, this angular velocity, we have got omega cos lambda zs plus omega sine lambda kds, right? And the velocity v, this vector is given by minus this small v represents the magnitude of v here. Just simply you can write v as we are using arrow here. If you use the arrow here, this bold letter represents the vector, right? This v dash, right? K dash. So you can consider that way. So here negative sign represents the body is moving vertically downward, so that's why this negative sign is given here. The purpose of negative sign representing the moving vertically downward. So while the positive z axis is vertically upward, right? So Coriolis force is given by Fc. So we have considered Fc, this one. This is the Coriolis force. Fc is equal to minus 2m omega cross v dash, right? So you have understood this. Now if you put the omega here from this equation, and if you put v also from this equation, right, then you will get this result. And from here you see we are getting I dash cap, so that means it representing the east direction, because along east we have taken x dash, right? So this equation represents that the Coriolis force in this case is acting along the positive x-axis. Therefore the deflection of the body that which is falling down will be towards the east in the northern hemisphere. So hope you have understood this. And this lambda here represents latitude. Okay, this lambda is the latitude here. So hope you have understood. So our next question is the relativistic energy. What is relativistic energy? So and we need to prove this relation as well. So here you see relativistic energy is the total energy of a body which is equal to the sum of its rest energy and relativistic kinetic energy. So here you can see two terms are there. You can see these two terms, m naught c square. M naught is rest mass, right? So and m minus m naught c square, this gives you the relativistic kinetic energy. So sum of these two gives the total energy E, and if you simplify this result, then you will get mc square, right? So this is nothing but relativistic energy. So here you see, now let's come to this next part of this question. That means we need to prove this relation. So here you see relativistic momentum is given by this equation, then the relativistic energy is equal to E is equal to mc square, where E is given by m naught, this is m naught by root over 1 minus v square by c square into c square, right? So here you see what we're going to do, that just squaring the both of these expressions. So first find the energy E square, and here square of momentum p square. Then what you can do, just we have done here, just we have multiplied by c. You can see we have multiplied c square here and here also. C square p square c square, and c square is multiplied on the other side as well of this equation, right? So then subtracting these two, just what we have done. So you can see here, let me clean this. So first we have multiplied c square on both sides. So if you see this equation, p square is equal to m naught square by 1 minus v square by c square, then again v square. So I have multiplied here c square and here also c square. Then this is subtracted from this equation. E square is equal to m naught square c to the power 4 by 1 by v square c square. So simply what we have done, we have multiplied c square on the both side of this equation. P square is equal to this one, m naught square into v square by 1 by v square 1 minus v square by c square. Then this is subtracted from this equation. E square is equal to m naught square c to the power 4 divided by 1 minus v square by c square. So these two equations are subtracted to get this result, and simplifying this, so hope you will be able to simplify being the student of BSc, so you will get this result. So hope you have understood this. So now let's move on to next question. Here we have a numerical. Calculate the momentum of photon whose energy is given. So it can be calculated using this relation. Here c is the velocity of light. So just put the velocity of light and the given energy of the photon, then you will get the momentum of the photon. Right, so that is your answer. So now let's go to the next question. Here is the relativistic Doppler effect. So this is the definition of relativistic Doppler effect. Is the change in frequency and wavelength due to the relative motion between the source and observer, right? This is all about relativistic Doppler effect. So now let's go to the next part of the question. Derive its formula using Lorentz transformation. Now let us assume that we have two frames. So I will give you the note, proper note. Just let me explain first. So we have taken two systems. That is S dash and another is S. Suppose another is S, right? So this is moving with respect to S with velocity v, suppose, and here we have a transmitter at the origin of the frame S, and we have a receiver here at the origin O dash of the system S dash. We have a receiver here, right? We have assumed that way. Okay, now you see, suppose this transmitter from this transmitter two pulses of light emitted, right? And the time interval between these two pulses received by this receiver be suppose del t dash, that's gonna be equal to suppose capital T dash. So we have taken capital T dash. So because here you see this first pulse was released when t is equal to 0, next pulse was released when this small t is equal to capital T. We have taken that way, right? Then you see this del t dash will be the interval between the reception of these pulses, which is for the observer or the receiver at this as this frame, right? And this will be the proper time interval t dash, right, between the pulses, since the observer or receiver is the receiver and s dash. This receiver at origin O dash, at the origin O dash R is at rest relative to this S dash, so that's why the distance x dash covered by him, x dash, and this x dash, that is the distance covered by the receiver or the observer relative to S dash, that's gonna be equal to 0 because it is at rest with relative to S dash. But the distance covered relative to this S frame, that's gonna be given by here you see, that's gonna be given by, let me tell you that you see c into t, right? So c is the speed of light into t, so that's gonna give you the distance, right? So because you know that distance is equal to time into speed, so then the what will be the speed of the light, right? What will be the time taken by the light, the second pulse, to reach the receiver? That will be t is equal to dx by c, because in time t, this is moving forward, and this after receiving the first pulse, the time will be taken by the next pulse. Second pulse will be t is equal to dx by c. So dx is the distance that covered by the receiver at s dash, which is at rest relative to s dash, but it is moving relative, it is in motion relative to s. So distance covered by this receiver with respect to s is dx, and that's why the time taken by the second pulse after the first pulse to reach the receiver is t is equal to del x by c. So hope you have understood these things. So let me give you in the written properly. So from here you can note just written everything whatever I have explained. Then let's go to the next slide. Here is you can see by inverse Laplace transformation, Lorentz transformation by inverse Lorentz transformation, we have got these relations del x, and here is the equation number 1. This is the equation number 1. So now let me add the next slide. So now this is equation number 1. Let me rewrite this equation on the next slide also. So what we have got, del x is equal to v into t dash by root over 1 minus v square by c square. This is equation number 1. So here is equation number 2. This is the next slide, equation number 2. This is equation number 2. Now what we have done here, so substituting the values of del x and del t from equation number 1 and 2 in equation number 3. This is the equation number 3. This is equation number 3. Now if you put 1 and 2 in this equation number 3, then what you will get. So let's move on to next slide. As you can see, I have written this relativistic formula of formula, Doppler's relativistic formula, in terms of frequencies. So it can be written in terms of wavelength also. That is lambda dash is equal to lambda root over 1 plus v by c divided by 1 minus v by c. That's what you will get, right? So because if you just here you see, if you take this equation, if you consider this equation, this one, equation number 5, this is equation number 5, you consider this. If you replaced nu by c by lambda, and if you replace nu dash by c by lambda dash, and nu is equal to c by lambda, then from equation number 5 you will get this relation, right? So this is in terms of wavelength, right? So hope you have understood. Now you see, one of my students remind me that I have missed one question. That means I forgot to give the answer of one question. First question number 1, last of the question number 1, MCQ. So this is the question. The special theory of relativity deals with the system. This one in part. This is supposed to be in part 1, but I have forgot to give the answer there. I have missed it. I skipped this question. Actually, I missed it. So its answer will be inertial system, right? This is your correct answer. So hope you have understood. And if you like my videos, then hit the thumbs up button and share with your friends. And if you are new to my channel, subscribe the channel. So hope you enjoyed the video. Then see you in the next video. Thank you for watching. Stay connected.